Hi, everyone. We're now going to go from tangent to cotangent. And what are going to be some similarities between these two functions? So similarities between cotangent of x, say, and tangent of x. Well, for one thing, their graphs are both going to be snakes. The period will be pi for both functions, and the VAs are pi units apart. Remember that for tangent, the basic tangent graph, the VAs here were pi units apart, and that was in fact the period. As a piece of wallpaper, period is pi, period is pi, period is pi, and there are pi units between the VAs. The same will be true for y equals cotangent of theta or x. Now, one warning, if you consider cosecant of x and secant of x, we're going to see that, again, VAs will be pi units apart, like for cotangent and tangent. However, but the period will be 2 pi for those later two functions, and also the graphs will not be snakes. But it is true that for the graphs of cotangent, tangent, cosecant, and secant of x, we are going to get pi units between the VAs. That also means that you're going to have pi units between the exclusions from the domain. All right. Now, how do we get from the graph of y equals tangent of theta to the graph of y equals cotangent of theta? Now, don't freak out about this, but we can consider these transformations. So what is cotangent in terms of tangent? By the cofunction identities, cotangent of theta is equal to tangent of the complement, pi over 2 minus theta. Remember that according to what I call the switch rule for subtraction, b minus a is the opposite of a minus b. So when we switch about the minus sign to get the theta in front, pi over 2 minus theta, that equals the opposite of theta minus pi over 2. And what can I do with this -1 factor on the argument? Tangent is what kind of function? Tangent is odd, which means that this -1 factor on the argument can pop out. Cotangent of theta is equal to the opposite of tangent of theta minus pi over 2. And right here we have a recipe to get from the graph of y equals tangent of theta to y equals cotangent of theta. Remember section 1.4 on transformations. In particular, if we substitute theta with theta minus pi over 2, I'll put that in red. If we substitute theta with theta minus pi over 2, what happens? We take tangent of theta and we substitute with theta minus pi over 2. We substitute. What happens? That leads to a horizontal shift. A horizontal shift to the right by pi over 2 units. We shift to the right by pi over 2 units. Although it turns out that shifting left would yield the same graph, technically we shift to the right by pi over 2 units. And if we multiply all this by -1, what happens? We flip the graph. We reflect the graph about the horizontal axis, say the theta axis. We do a flip. So how can we get from the graph of y equals tangent of theta to the graph of y equals cotangent of theta? We take the original tangent snake graph, shift right by pi over 2 units, and reflect, flip, about the horizontal axis. So, bottom line, we shift to the right by pi over 2 units, and we reflect about the horizontal axis. So you see, these tangent snakes shift right. The VAs also shift right by pi/2 units. And these rising snakes flip over and become falling snakes. We have a shift and a reflection to get from the tangent graph to the cotangent graph. Still, the period is pi units, and the VAs are still pi units apart. The range is still all reals. That does not change either. Okay, so how do we graph one cycle for y equals cotangent of theta? Well, remember, before for tangent, we had VAs at theta equals negative pi/2 and theta equals pi/2, corresponding to the north and south poles on the unit circle. But now, we're going to take these VAs and shift them to the right by pi/2 units. So negative pi/2 goes to 0, and pi/2 goes to pi. Over here, we have VAs at theta equals 0 and theta equals pi. As a result of that, the pivot is not at the center as it was for tangent. We're back to the left center, like for sine and cosine. We associate the origin now with the left center point on the frame, as we did for sine and cosine, although this point will not be a point on the graph. We have our frame here. We have VAs at theta equals 0 and theta equals pi. Instead of a rising snake, remember, we have a falling snake. So we pick up these 3 key points here, tic-tac-toe, but they're falling this time. And we have VAs to the left, so the snake rises to the left. We have a VA on the right here. The snake falls to the right VA over there. It's a falling snake with 3 key points tic-tac-toe along this diagonal. For tangent, we went tic-tac-toe along a rising diagonal. So here are 3 cycles for y equals cotangent of theta. Again, the period is pi units, and we have pi units separating the VAs. But unlike tangent, we have VAs at 0, 1 pi, 2 pi, integer multiples of pi, and these are falling snakes, not rising snakes. But like tangent, cotangent is odd. So we do still have symmetry about the origin. If you take this graph and rotate it 180 degrees about the origin, you get the same graph. All right. Now, there's another way of looking at the relationship between tangent and cotangent. One is from the cofunction identities, where we got the ideas of shifting and reflecting, but we can also look at these 2 functions as reciprocal functions. And we're going to devise principles of reciprocal trig functions that we're going to apply later when we discuss y equals tangent of theta, or sorry, y equals cosecant of theta, and y equals secant of theta. So what are these principles of reciprocal trig functions? Okay, now when tangent is 0, what is cotangent? What is 1 over 0? 1 over 0 turns out to be undefined. So remember that whenever tangent is 0, cotangent is undefined. We have a VA. When tangent has an intercept, tangent is 0, tangent is 0, tangent is 0. Over here, and over here. These correspond to VAs for the cotangent graph. Intercepts for the tangent graph correspond to VAs for the cotangent graph. When tangent is 0, cotangent is undefined. And also vice versa. When cotangent is 0, tangent is undefined. When cotangent has a theta intercept, tangent has a VA. So theta intercepts for one graph lead to VAs for the other graph. So for these reciprocal trig functions, remember that one function is 0 in value if and only if the other is undefined. That is, we have an intercept like an x or theta intercept for one graph, when we have a VA for values of theta, where we get VAs on the other graph. Okay, now what about signs? Well, the reciprocal of a positive value is still positive. For example, in quadrant 1, all these guys are positive, right? When tangent is negative, so is cotangent. A reciprocal of a negative is a negative. So as far as reciprocals go, positive goes to positive, negative goes to negative. Positive to positive, negative to negative. So reciprocals have the same sign for the same value of theta. Okay, in between the VAs and the intercepts, the zeros. So between the VAs, where the functions are undefined, and the intercepts, where the functions are 0, the values of reciprocal trig functions have the same sign. For example, in quadrant 1, both tangent and cotangent are positive. In quadrant 2, between pi/2 and pi, both tangent and cotangent are negative. For tangent, we're crossing a VA. For cotangent, we're crossing an intercept, a 0. Same sign. To make things cleaner, I'll erase these now. All right. What about increasing versus decreasing? Again, between intercepts and asymptotes, as one function increases, the other function, look at this, decreases. For example, in quadrant 1, tangent increases, slope increases as you go from 0 to pi/2. But cotangent decreases. Think about this. Let's say that tangent is going from 1 to 2 to 3. The slopes are going from 1 to 2 to 3. What's happening to the reciprocals? The reciprocals are going 1, 1/2, and 1/3. So as the tangent values increase, the cotangent values, the reciprocal values, decrease. They go in different directions. In quadrant 2, tangent is still increasing, but cotangent is decreasing. In quadrant 3, well, tangent is increasing along these snakes, cotangent is decreasing along its snakes. So in between the asymptotes and the intercepts, as one function increases, the other decreases. As one function increases, the other decreases. I'll put this in purple. As one function increases, the other decreases, and vice versa. They go in different directions. Again, that corresponds to the fact that tangent has rising snakes, while cotangent has falling snakes. Also, they have the same period. For example, you can see that you have pi units between the VAs, and the snakes have width pi units. But as I mentioned earlier, we're going to see that for the cosecant and secant graphs, that, again, the VAs will be pi units apart, but the period will be 2 pi and not pi. Those graphs will not be snakes anyway. Okay. So let's talk now about domain, range, and vertical asymptotes. First off, the range. You can see that the snakes are going to be infinitely tall, both up and down, so it's not surprising that the range is going to be all reals, like for tangent. But the vertical asymptotes and the domain are going to be shifted by pi/2 units. So remember, because cotangent of theta, by the reciprocal identities, is 1 over the tangent of theta, cotangent is undefined. Cotangent is undefined if and only if tangent is 0. Cotangent is undefined exactly when tangent is 0. When is tangent or slope 0? Well, we're going to have our problem points at the east point and at the west point, corresponding to this horizontal line through the origin. slope or tangent is 0 at the east point and the west point. And what are the angles that we associate with the east point and the west point? Well, angles like 0, pi over here at the west point, back here, 2 pi, also 4 pi and 6 pi, and the opposites. Over here, we have problems at 1 pi. We have problems at 1 pi, 3 pi, 5 pi, and so on, and their opposites. Basically, integer values of pi. We're going to have problems at integer multiples of pi. Integer multiples of pi. 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, and so forth, and also their opposites. -1 pi, -2 pi, and so forth. Those are our problem values for theta. That's where tangent is 0 and cotangent is undefined. Cotangent of theta is undefined if and only if tangent of theta, the slope, is 0. That's where theta is pi n. Integer multiples of pi, where n is some integer. N is in Z. The set of integers. Half revolutions. The problem angles are separated by half revolutions, just like for tangent, where we had problems at the North Pole and the South Pole. Again, another way of looking at that, if you tear apart cotangent, cotangent of theta was cosine of theta over sine of theta by the quotient identities. Tangent had a problem when cosine was 0. Cotangent has a problem when sine is 0. And where is sine 0? Where's the y-coordinate 0? The y-coordinate is 0, again, at the west point and the east point. Another way of seeing that those are the problem points, and these angles here are the problem angles, because we do not want y to be 0, sine to be 0. Okay, so cotangent is undefined when tangent is 0, the slope, also when sine is 0, the y-coordinate on the unit circle. Either way, here are the problem points. The domain, therefore, is a set of all theta in the reals such that theta is not, remember, is not of the form pi n for integer values of n. Here's the shorthand. The range is all reals, just like for tangent. Infinitely tall snakes, up and down. All right. Next up, we're going to graph tangent and cotangent functions more generally using Picapia, the frame method. And we'll talk about that next time.